Knowledge Biology. This is Energy Carriers Part 3. In Part 1, we introduced the concept of energy carriers and what the cell might use them for. In Part 2, we discussed spontaneous reactions. Since energy carriers can be used to drive non-spontaneous reactions, we had discussed what a spontaneous reaction is and the terms endergonic and exergonic, since they are important to spontaneous reactions. In this video, we're going to discuss how ATP can be used to actually drive those non-spontaneous reactions. So let's take a look at ATP again. ATP, as we know, is this molecule here. It's a modified nucleotide. It has a purine, which is adenine. It has a sugar, which is ribose, and it has 3 phosphate groups. Now you'll note these phosphate groups, each phosphate has a negative charge. And we know that for the rules of electromagnetism, like charges repel. So right now, these negative charges are bound together by these covalent bonds. But we know about hydrolysis. We know that if water comes along, we can break this bond with water. We can break the bond into 2 particles, and that's what's happening here. We've got our ADP here with 2 phosphates, and then we have our phosphate, which has been released. So a hydrolysis reaction can be used to turn ATP into ADP. Now let's take a look at what happens to energy when this small reaction occurs. Right now, this is a graph of the energy of these molecules. We have this much energy in ATP. We've got this energy. This is where the hydrolysis occurs. Then these molecules lose energy, and this is where the energy state is in ADP. So we have this much energy stored chemically in the ATP. We have this much energy stored chemically in the ADP. Where did all of this energy go? Well, this is an exergonic reaction. That energy went out into the environment as heat and motion. Well, how did that happen? That comes back to this situation with our negative charges. As soon as this bond gets broken, that phosphate shoots out because these negative charges repel it. So the bond breaks and pshoo, that phosphate shoots out into the world. As it goes out into the world, because it was chemical energy, now it's being transferred as sort of kinetic energy. So now it's going out there, it's rubbing up against other molecules that it passed by, it's transferring some energy as heat. Maybe it's pushing molecules, pushing them as kinetic motion. So now there's more energy outside in the environment because this phosphorus was shooting through there, transferring its energy to everything it touches. Now, with more energy in the environment, maybe some of those molecules are moving around a little bit faster, they have a little more harder collisions, they overcome some activation energy, and they start doing reactions. That's a possibility. So that's one way that we can increase the energy in the environment just by releasing that phosphate through hydrolysis. There's some other things that can be done with phosphates. If this phosphate gets attached to a protein, maybe it'll cause an isomerization to occur, protein will change its shape, and maybe it'll be able to do a reaction, I don't know. But that's something that you can do with phosphates, but just releasing the phosphate itself releases energy into the environment. How much? Well, they've got this value here, 7.3 kilocalories per mole. But that's kind of a big deal. ATP stores chemical energy, and then when it goes under hydrolysis and it releases that phosphate, that energy is released. Well, what can we do with that? Well, to put that phosphorus onto the ADP in the first place, we needed some energy. We needed to store that energy in that chemical form. So energy from exergonic reactions, other exergonic reactions in the cell that are releasing energy, can cause ADP to be phosphorylated to make ATP. And now all that energy that was exergonic is stored as ATP. Not all of it. A lot of that energy that is exergonic. Some of the energy from exergonic gets out into the environment as heat and motion and is not recaptured. But some of it gets recaptured by ATP. Now, ATP can be moved. It can be moved to a place where there's going to be an endergonic reaction. Here, let me shift this over. It can be moved to a place where there's going to be an endergonic reaction because it's got this stored energy from this exergonic reaction that happened over here, stored it in ATP, moved the ATP, and then we can undergo hydrolysis and release that energy. And now that it's releasing energy, the endergonic reactions that need to absorb energy can take the energy that ATP releases and then do their thing. So ATP is an energy coupler. It unites it takes energy from exergonic reaction and stores it, and then couples that with an endergonic reaction and releases the energy for the endergonic reaction. So our cells very efficiently and conveniently find reactions that are absorbing energy, try to recapture some of that, move it to a reaction that needs energy, and releases it for them. That's what ATP does. That's what an energy carrier does. I hope this helps. Struggle well.